Okay, this is our lecture number 14, and in this lecture we're going to continue talking about hypothesis testing for numerical data, and also we'll look at the testing of the hypothesis with the categorical data. So, next problem. Customer service. For the past few years, the number of customers of a drive-up bank in New York has averaged 20 customers per hour. This year, another bank just 1 mile away opened up a drive-up window. The manager of the first bank believes that this will result in the decrease of the number of customers. So, a competitor opens up pretty much right next door. That means that some, probably customers, will switch to the new bank. They will transfer their money and their accounts to the new bank, and therefore you will see less of the requests, less of the customers per hour. So what happened is the manager of the bank decided to record how many customers are coming every hour during 36 randomly selected hours, and the results are recorded in the file bank.csv. So here's the question in the problem, the research statement. Can we conclude at 5% significance level that the manager is correct? What does that mean? Well, he is afraid that the average number of customers that are coming every hour to the drive-up window will reduce, right? Here I have underlined statement decrease in the number of customers. So it was 20 historically, and now he's thinking that it dropped from that number lower, so it's something less than 20 per hour right now. Okay, so let's jump at the data set. So I'm gonna call it bank_data and read the CSV file. Data recorded in the file C data folder bank.csv. Okay. And again, oftentimes it's a good idea to take a look at the structure of the data, right? Structure of the bank_data. All right, there it is. I'm gonna give a couple of entries. The data frame, bank data, contains 36 lines, 36 observations. Well, we knew that from the problem. And one column, one variable. Variable is called customers. It's probably was better to call it number of customers, but yeah, okay. And it is integer. Well, that makes sense, right? Because we're tracking number of customers every hour, and the only thing that can be is just a bunch of integers. So long story short, it's a categorical. It's a numerical data. Okay. So here I'm gonna leave a comment. Explore data structure. Well, first things first, we probably are going to end up doing hypothesis testing, right? Now, so far we know the only thing that can be done with hypothesis testing, and that is doing the t-test. Okay, doing t-test on one sample of the data that came from one single population. Okay, so, and we know that we have to check the required conditions, right? In order for us to be able to meaningfully use the concept of the mean or the average, population average, the data has to be normally or close to normally distributed, and therefore sample, which is just a small representation of the data of the population, it also has to be approximately normally distributed. So we agreed so far to do that in a couple of ways, right? So way number one is we're going to, so here I'm going to leave a comment, right? Check data for normality. Check data for normality. And well, quick and dirty check is to look at the histogram. So let's take a look at the histogram of bank data. $, the only column customers. So here is my picture, right? It's not the most normal data that I've seen, but at least it's unimodal. There's only one peak, and it's, well, roughly speaking, bell-shaped. I can see some imbalances between the right side and the left side, but that's not something terrible. So I think that the data, at least on the on the picture, it looks pretty much normal. All right, so let's perform more rigorous Shapiro-Wilks test. So when I start typing Shapiro, here's the name of my test, and it's very easy to use, right? So I have to send the function Shapiro.test, the column, which is bank underscore data customers. All right. Okay, so reminder, here's what I'm testing, right? In the Shapiro-Wilks test. Null hypothesis is always that the data are normally distributed. Alright, and the alternative is data opposite of normal, opposite of null, right? Data are not normal. Okay, so p-value is right here, right? 0.468. 468. And we have agreed in the previous lecture that every time when we use the Shapiro-Wilks test for normality, we're going to use the significance level, standard level of significance 5%. So in this case, I can see that my p-value is higher than 5%. Here I'm going to say standard value of significance level. Okay, so what does that mean? That means that I do not have enough evidence in the sample to reject the null hypothesis in favor of alternative. Null stands, and therefore data are normally distributed statistically. So these imbalances, they're due to randomness, right? Customers come in every hour, and this is the process which is I can't control really. From hour to hour is going to be different. It will depend on individual people's needs in terms of cash, or they want to deposit something, or they want to deposit the check, whatever it can be, right? Open new account. I don't control really the process of arrivals, so therefore due to the random nature of arrivals, it cannot be perfectly normal, but statistically it's pretty much normal. Okay, so now what I'm going to do is formulate what exactly is that I'm testing, right? So let's go back to our slides right here. All right, so and the next slide basically discusses what we just performed, right? We looked at the histogram. Histogram doesn't look very horrible. It's approximately normal, and we performed the rigorous Shapiro-Wilks test, and it indicates that data are normally distributed. So what are we testing? Well, it's always, I told you that always look for the challenging statement, for the research statement, right? What is that we're trying to find out? The manager believes that the opening of the competitor just down the road will result in the decrease of the number of customers from what it was before. And before it was 20 people per hour. And that becomes our alternative hypothesis, right? So your research statement is always the content of your alternative hypothesis. So therefore my alternative is going to be this. That the mean, new mean, average number of customers that come in every hour is now less than 20, less than what it was historically. That's exactly what I'm testing. So opposite of that becomes my null hypothesis, right? So null is, again, remember, null is status quo, right? It's the statement that reflects the world kind of in its normal, comfortable state, right? Normal is to see 20 customers on average per hour. Okay, so and that becomes my null hypothesis. If the average is 20 or maybe even more, which is better, then no problem. The opening of the new competitor down the road did not steal business away from us. Okay, that's what we're testing. So important thing here is that my alternative has the form less than. All right. So well, where there is a fire, there should be a smoke, right? So the alternative that we're checking is we suspect that the average number, the true population average number of customers per hour, is now less than 20. The evidence is my sample, right? We discussed that the hypothesis testing is very similar to the criminal court, where there are two statements and the evidence is brought in order to see if the alternative statement is true or maybe not. So in my case, evidence is the sample itself, and the evidence should come in the form of, for example, X bar, right? So if the manager believes that now I see less customers per hour, then from the sample analysis I should see the average of less than 20. And if that's the case, that would be kind of sort of an indication that the alternative might be right. So I suspect a fire, mu less than 20. Do I see the smoke? And the smoke comes in the form of X bar, right? So let's go ahead and compute the mean for the column. That would be bank data in the column customers. And I can see that the average is in the sample. Of course, this is not a population average. This is a sample average, right? So the average is 19.277, close to 19.3. All right, so, and that's the smoke, right? So my average, it does point me sort of, kind of, in the direction of the alternative hypothesis. So I'm looking at this X bar and I'm saying, well, maybe the manager is right. Okay, so now I have to test my hypothesis, obviously, right? Just like always, let's go ahead and I'll leave a comment here. I'm going to use a t-test, right, to test hypothesis that new average, new population mean is under 20 customers per hour. Okay, so and we're going to use pretty much the same same t-test that we used in the two previous problems. So I'm going to say t.test. All right. And in this test, first of all, I have to provide the function with the column of data, right, that I'm going to test. So that would be bank underscore data $ customers. Okay. Then I have to specify what's the mean that I'm hypothesizing. So it's the number from my null and alternative hypothesis. So I'm hypothesizing that the average is 20. That's my null, right? And alternative is less than, right? So I'm gonna switch to the PowerPoint. So here's my alternative. Okay, I'm assuming that now the new mean is less than 20 customers per hour. Okay, yeah. So and this is what we're going to do: test t.test bank data customers. The average is 20 and alternative is less. All right. I'm going to run this line again. It tells me that the average of the x in my sample, right? Again, this is not a population average. This is a sample average. Okay. But important thing is right here. My p-value is 0.07232. All right. Let me switch back to the to the PowerPoint. Here the problem instructed us to use 5% standard value of the significance level. Okay, so at 5% significance level, do I have enough evidence to state that the new population mean, new average number of customers coming every hour is less than 20, and therefore the bank down the road might be stealing customers away from me? Well, my p-value is 0.07 and it's greater than 0.05, right? What happens if I have p-value higher than the significance level? I fail to reject the null hypothesis. So if I fail to reject the null hypothesis, then between the null and the alternative, I'm going to say there is not enough evidence to reject the null, so I'm going to still believe in null. If you remember, we discussed that in the previous couple of lectures. The hypothesis testing always starts with the assumption that the null is true. So I started that test with the assumption that the true average number of customers per hour is still 20 or even more than that. So my p-value is high, therefore the number that I have observed, 19.28, is not that far away from the hypothesized average 20. So a sample like that will every once in a while come up, right? And it will come up in 7.23% of the cases. It's not a rare event because my measure of the rare events is alpha, significance level, right? 5%. Anything below 5% is low probability. Anything above 0.05 is not so low probability. So this sample is not that rare because its p-value is 0.07. So therefore I fail to reject the null, and I'm going to say this sample does not provide me. The sample collected does not provide me enough evidence to conclude the true average number of customers per hour. The drive-up window is now less than 20. So the sample that I see is fairly consistent with the true population average of 20 or above. So in other words, I still believe in the null hypothesis. I failed to reject it. Even though there was a blimp, right, on the radar, I took the sample and the average in the sample was 19.28. That by itself is not an indication of the problem yet. Okay, I tested the hypothesis and this number is not that far away from 20 for me to ring the alarm bells. Now, the last piece of the puzzle is I want again to show you, just like I did in the previous two problems, what is the interpretation of the p-value. In the previous couple of lectures we discussed that the standard interpretation of the p-value is it is a probability. Okay, so oftentimes when I ask this question actually on the exam, more often than not, unfortunately, I start seeing the answer like p-value is less than alpha, so therefore reject the null, or it's greater than alpha, so we fail to reject the null, and therefore we believe that this happens, that happens. No, that's not the interpretation of the p-value. This is how you use the p-value to conclude the test. But the interpretation of the p-value is always a probability. That's why it's called p-value, by the way. The letter p in p-value stands for probability. So p-value is the probability to see the sample as extreme as you are seeing in the sample, the average as extreme as what you're seeing in the sample, or even more extreme than that, if the null hypothesis is true. This is the generic interpretation of the p-value. Okay, probability to see sample as extreme as that, or even more extreme, given that the null is true. So, given that the null is true, our average is 20 or above, right? So, if the true population average is at 20, that means that this is how the sampling distribution will look like. This is important, actually, connection with what we discussed about 3 or 4 lectures ago, sampling distribution. Why is that so important? Sampling distribution, we saw that if you take a lot of different samples of the same size from the population, and you calculate averages and plot them on the same graph, all these averages. Property number 1 of the sampling distribution was that whatever the population mean was, sampling distribution will have exactly same mean. So, if my population average, mu, is 20, it's going to be the same for the sampling distribution. So my sampling distribution will be peaking at the value of 20, okay? And every time when I get a sample of customers, 36 in this case, right, I'm going to get a different X bar. But as I get more and more samples, 36, 36 others, 36 others, 36 more, etc. And for each I calculate the X bar, they'll start form shape like this, right? This is the distribution of all possible X bars. So this is a sampling distribution. And but I got only one sample, right? Really, all I had was these specific 36 people. Sorry, it's not people, it's hours, right? 36 hours out of the bank's operations. And my X bar was 19.28. So it's right here. It's on the low side, right? So p-value is the probability to see a sample like that, 19.28 X bar, or even more extreme than that. What does that mean, more extreme? It depends on which alternative you're testing. In my case, I was testing less than, right? That the mean is less than 20. So that means that I was testing the left tail of the distribution. So specific to that problem. More extreme than that means even lower x bar. So all the area in the left tail of the distribution is my p-value for that specific problem. Okay. So therefore, graphically speaking, it's the area under the well, yeah, it's probably close to normal, right? Curve is close to normal. That's my sampling distribution, and it includes all the values to the left from 19.28, right? And the fact that I'm starting the testing of the hypothesis with the assumption that the null is true, on this picture it's indicated by the fact that my population, my sampling distribution has the peak at the value of 20. It's the same as the population mean, which I hypothesized in the null hypothesis. Okay, so that concludes this this problem. So we looked at 3 different examples, right? First was about in the previous lecture counts, right? So was the average count above 170 or was it not? So we looked at how to test hypothesis when the alternative is greater than 170. The second problem that we looked at is skiing, right? How many days on average a skiing enthusiast per year spends in mountains just doing skiing, right? And it was, is it 5.5 or is it not 5.5? And because the alternative was not very specific, it's like not equal. Okay, what is it? Is it greater than? Is it less than? Which one? Well, it's both actually. Okay, so it was two-sided test, and in this problem we looked at less than. Alternative was less than. So we covered pretty much all 3 grounds. So that concludes basically analysis of hypothesis testing for the numerical data. Now let's take a look at the case with categorical data. So next problem. All right, so let's first of all customer service problem. Yeah, it's the same one, right? So here, this one. So let's discuss what happens with the categorical data. Well, for categorical data, you remember that probably. We repeated that in these lectures again and again and again. The calculation of the mean does not make any sense. The reason is very simple, because the numbers that we assign to different categories are subjective. They're our choice, right? For example, in the elections, we can code Republican as 1 and Democrat as 2. Or alternatively, we call Republican -1 and Democratic candidate +1, or we can call them 10 and 20. It doesn't really matter. Okay, these are not actual numbers, these are labels, just so that we can record data easily. Instead of typing each time Democrat or Republican, we just say 1 or 2. That's it. So the numbers that we assign to different categories are just labels. They have no meaning attached to them. Okay, so therefore, if we calculate the average has no meaning. So for categorical data, nominal or ordinal, calculations of the averages doesn't make any sense, and therefore we cannot use that, right? So what exactly are we testing? Well, we discussed in pretty much our second or third lecture that for categorical data, pretty much the only thing that can make sense is number of responses or proportion of responses in different categories. For example, proportion of people who voted for a Republican candidate or Democratic candidate. Or another good example is manufacturing. In the manufacturing process, you have machine, right, that makes different parts, and each part can be tested after it's been finished. And upon testing, upon final testing, we can determine if this part is good or if this part is defective, right? So if it passes the inspection, the quality check, then we'll label that as good. If it fails certain aspects of the quality check, then we'll label that as bad, okay? So therefore, each part, just like on elections, right? Each voter cast their votes either for Republican or for a Democrat. Same thing with parts. Each part is either good or bad. So in this case, we can calculate percentage of defective parts, right? And that would be an important characteristic of the machine, right? What percentage of the parts are normally defective, that are manufactured out of 100% parts out of the entire population. Okay, so if proportions is the only thing that we can calculate, then here's what happens. Okay, when we're testing the proportions, we're getting a sample again, just like with the exit polls, right? Exit poll is just people standing on the outside of the exit place, outside of the voting place, right? And they're asking a number of people, did you cast your vote for Republican or did you cast a vote for Democrat? They can't ask 100%, so it's a sample. We pick how many people we're going to poll, and we stick with that number, right? So n is the number of items, so the sample size. So out of these n items, let's say x is the number of items that are of interest for us, right? Or for example, we're looking to find out what percentage of people voted for a Republican candidate. So we ask 750 people, and we record, we track how many of these 750 answered, I voted for a Republican. Or take the machine example, right? We essentially tracking, we can't track every single detail, even though with the development, actually that might be not true anymore, right? I mean, 50 years ago, that's for sure, right? We could not track possibly and test every single part that we're manufacturing. With modern technology, oftentimes it becomes possible actually to do the 100% quality check, okay? But that's beside the point. So let's say I'm just selecting n items, right? And each item, I'm going to run the quality test on the item, and at the end of the test, I'll have, yeah, this part is good, or no, this part is defective, it needs to be scraped or reworked, or whatever I do with the part, right? Downgraded, it's like second grade part or something like this, okay? So therefore, from the sample, we can calculate and point estimate, right? Because we're not testing every single part, we're testing only selected number of the parts. The ratio of parts we found defective out of all the parts that we tested, that's our just sample point estimate of the true population proportion, right? If we could test every single part that we're manufacturing, or we could ask every single person in the state, who did you vote for, then we're going to get an actual true population proportion. And we're using Greek letters, right? Pi for the proportion and mu for the mean. Okay, so, and since we're settling for the sample, we also discussed that before, right? You pick different n parts or different n voters, number of defective parts out of n, or number of people who voted for Republican out of n, will be different for a different sample. So therefore, your p hat, each time when you pick a sample of size n, your p hat will change its value. So therefore, all possible p hats form their own distribution, which is also called sampling distribution. Okay, so sampling distribution does not just apply to the numerical data when we're dealing with population mean and sample means. It also applies to the categorical data when we're dealing with population proportion and sample proportion. Actually, we discussed that exactly in the lecture, I believe it was 2 lectures ago, when we talked about estimating the confidence interval for the population proportion. And the example that we used was precisely the one with exit polls, right? So we, if I remember correctly, the sample proportion for people who voted for Republican was 0.532, 33.2% voted for Republican, and we wanted to construct upper and lower confidence interval for a 99% or 95%, I don't remember, confidence interval, right? And we used the fact that all different p hats are distributed approximately normally around the true population proportion pi, with the weird looking standard deviation. And this is what exactly I put on the next slide, okay? So if we pick different samples of size n and calculate sample proportions, point estimates, p with a hat, they're all going to be distributed approximately normally around the true mean pi for the population, and the standard deviation that looks like this. True pi times 1 minus pi divided by n, square root from all of that. Okay. So, and we're going to use that fact actually in order to test the proportions. Okay. So for hypothesis testing in proportions, we're going to do pretty much very similar stuff, very similar test, but it's not going to be the t-test, it's going to be something else. It's going to be a special actually function from R called prop-test, test for proportions. Okay, so I'm gonna skip that slide and go straight into the problem. Before we begin with this problem, let me point out that we discussed that for hypothesis testing for the mean, we have three different forms of hypothesis, right? Null and alternative. Null can be greater than or equal to, alternative less than a number. Another form is null can be less than or equal to, alternative greater than a number. And the last form, null is equal to a number, alternative not equal to a number. So null and alternative, they're always opposite of one another, and if you put them together, you get 100% of all possibilities. Guess what? Exactly same three different forms of hypothesis testing apply for the cases with proportions. We can test pi greater than or equal to a number versus less than or equal to a number versus greater than, or equal versus not equal. So same exact three forms we can test with proportions. Now, without further ado, let's concentrate on this problem. State Farm Insurance Company says that at least 90% of its customers who file insurance claims are satisfied with how the claim is resolved at the end. Now, I want to point out at least 90% means what? At least means 90 is lowest number, could be more, right? At least 90 or above. That's their claim. The company that conducts annual claimant satisfaction survey is somewhat skeptical about this and would like to check the accuracy of this statement on their own. So they conduct a survey of customers who were known to file claims in the recent past. The customers were asked, each one of them, if they're satisfied with the quality of service, how quickly the claim was resolved, how accurate was the assessment, did the company process this, so did they receive the payment, etc., right? Did the customer receive the payment? All these aspects, right? So are they okay with how State Farm Insurance handled that, or are they not okay? So in the file we have a bunch of responses, satisfied versus unsatisfied, right? And the responses are stored in the statefarm.csv. Okay, here is the research question, right? Here's the purpose of this whole hoopla. Can we conclude at 5% significance level that satisfaction rate is less than 90%? Okay, so originally the State Farm Insurance says that the satisfaction rate is 90 or above, but we're skeptical, so therefore we're going to conduct our own survey and find out if the actual true percentage or proportion of people who are satisfied with the claim is under 90%. Okay, so this is my research statement. And therefore, it becomes part of my, it becomes plain and simple my alternative hypothesis, right? Again, when you read the problem, always look for the challenging statement, for what is that we're trying to investigate. This will become your alternative hypothesis. So in our case, is what we're doing is we're trying to find out if proportion of customers who said that they're satisfied is not quite as high, not quite 90%, it's less than 90. Now, because proportions are decimal numbers, right, between 0 to 1, which corresponds to 100%, 90 is 0.9 really in the proportions world, right? And that becomes my alternative hypothesis, that the proportion of satisfied customers is under 90%. Well, then I reverse that statement and my null becomes proportion of satisfied customers is actually over 90%. Okay, 90 or above. That's what State Farm Insurance claims, right? So at the end of the day, when I conclude the hypothesis testing, I will have to pick between null and alternative, right? I start again by believing that the null is true, right? innocent until proven guilty. This principle applies to the hypothesis testing. So, and my goal of my investigation is to find out if the sample that I collect provides enough evidence to stop believing the null hypothesis and switch over to the alternative hypothesis. Okay. Now, important distinction that we are going to discuss right now is in the previous two problems, I tested the sample for normality, right? And I did that in two different ways. First, we looked at the histogram. If the shape is normal, then we're okay probably. And also we conducted the rigorous Shapiro-Wilk test. This is categorical data, right? So, in fact, let's go ahead and get started with this problem. Let me show you what the data looks like. So I'm going to put a bunch of pound signs here, separating one problem from another. State Farm, right? Okay, so first things first, data, right? State Farm data is read CSV, C drive data folder, State Farm, I believe, right? State farm.csv. Okay, yep, I got it. And let's take a look at the structure. str of the State Farm data. Alright, so what does it say? It says that I have 177 observations. That means customers, right, that were included in this survey. Only one column, only one variable, and the column is called rating, and there are only two possible values there, right? Satisfied, well, they're all satisfied right there, but another one is unsatisfied, okay? So, data are not numerical, data are categorical. Well, that's not a big surprise, we knew that. Well, big question is, do we test normality? The answer is no. Because in order for you to test for normality, you have to be able to calculate the mean, the standard deviation. None of that is possible with categorical data. Whether it's ordinal or nominal, it doesn't really matter. There is no such thing as mean, there is no such thing as standard deviation. Therefore, there is no such thing as normal in the world of the categorical data. Okay, so therefore our task is somewhat simplified, right? We can skip, well, it's not that we can skip, we have to skip the normality test and go straight into the testing of the hypothesis. But before we do anything else, let's take a look at the point estimates, right? Remember in the previous problem I told you, we suspect that, so here I'm testing my null hypothesis is that the true proportion, right? I'm going to use the letter P, okay? Or pi, okay? Pi is greater than or equal to 0.9. That's what State Farm is claiming, right? We are skeptical about that, so therefore we're saying, well, I'm going to see if actually opposite is true. If the true proportion of the satisfied customers is less than 90%, okay? So I suspect the fire. So this is the fire, right? Suspect that they're overstating their satisfaction numbers. Well, where there is a fire, there should be a smoke. So let's check for the smoke, right? Let's accumulate. Let's calculate statistics, summary statistics about this specific sample. Okay. So here is what I'm going to do. First, tabulate the data. So State Farm summary. So I'm going to summarize yes responses versus no responses, right? And that is done by calling on the function table. Okay. And what am I tabulating? I'm tabulating State Farm data column ratings. Okay. All right. Let's see what the summary looks like. State Farm summary. Summary says that out of these 170, I can remember right now what 177 observations, 153 were satisfied and 24 had complaints. Okay, cool. Now, one thing that I want to point out, I did point that out before, reminding. Okay, these are categories, right? Satisfied and unsatisfied are categories. The way how R represents the categories is purely alphabetical. That's it. For us, satisfied and unsatisfied means something, right? It's customers, they're happy, they're not happy, that kind of stuff. For software, such as R, doesn't really matter. That's meaningless for the software, okay? So categories are listed in an alphabetical order. That's why S comes first, satisfied, and U comes second, unsatisfied, okay? So, but I'm testing the hypothesis about the proportions, right, not the count. So therefore, let me go ahead and do the calculate the counts, right? State farm, let me call it proportions, right? Okay. Oh, I couldn't come up with anything better than that. All right, proportions prop dot table, and I have to send the function prop table the vector of the counts. Reminder, this is a vector, right? Remember, vector is a variable that points, it's a one single name that points to multiple different values, right? In my case, it points to the values 153 satisfied and 24 unsatisfied. So here, actually, I'm about to calculate yet another vector, but it's the vector that consists of proportions, right? But I have to send the vector of counts to the prop table. So state underscore farm summary, right? And there you go. So let me go ahead and see what state proportions are set. They're telling state underscore proportions. Alright, so here are the proportions. It looks like in my sample of 177 people, 86.4% said that they're cool with how their claim was handled, and 13.6% are unhappy with how their claim was processed, right? So my alternative that I'm testing is the true satisfaction rate, the true population proportion of satisfied customers, is less than 0.9. Do I have kind of sort of confirmation for that in my sample? Yes, I do, right? In the sample, my proportion of satisfied customers was 86.4, which is less than 90. Now the big question is that difference big enough for us to small that this is not an accidental find, right? What do I mean by that? We discussed that every time when I pick a different sample, my proportions are going to change, right? Just because, you know, randomness, okay? I pick 177 different customers, and instead of 153 unsatisfied, all of a sudden I have 68, all right? Next sample is going to be 144. It's going to be different each time I pick a different sample. So could it be that this proportion I observed purely by the chance? Okay. So in other words, how likely is that to see sample like that, or even more extreme, given that the null is true and the true proportion of satisfied customers is still 90%, right? So I'm starting by believing the null, and I'm going to calculate the probability to see a sample with the percentage of satisfied customers 0.8644 or less if the true proportion is equal to 0.9, right? Null is true and the true proportion is 90% at least. Why less? Because that's the form of my alternative, okay? Now for that we're going to use the new function, okay? So yeah, on this slide I basically repeat what I just said, okay? And this function is going to be prop test. So we're learning more and more functions, right? So for the numerical data, when it's normally distributed, we're using t-test, and this is going to be prop test. Now prop test, as you can see, takes several parameters. Number one, it should give me the count I should give the function the count of the responses that are of interest for me, right? In my case, it's the responses satisfied. Then I have to give it the number of observations, or sample size, simply, right? Then hypothesized proportion, as it was hypothesized in the null hypothesis, right? That would be 90% or 0.9. And alternative, I have the same selection. Just like for the t-test, t.test function, my options were less, greater, and 2-sided, right? So for the proportion testing, I'm doing pretty much exactly the same. Okay, have same options for the alternative hypothesis. So let's go ahead and find out how likely is that to see the sample with the proportion 0.8644 or less if the null is true, and the true proportion in the entire population is 0.9 or 90%. Okay, so proportion testing. Okay, so prop dot test. Now here I could basically do the following, right? What is the count of my satisfied in my sample? Count was 153, right? Comma. What's the sample size? I know that the sample size is 177. Okay. What is the proportion P that I'm hypothesizing? That's 0.9, right? And what's the alternative? Alternative is, as I can see, less than, right? Less. I could run the test like that. Here's my p-value, 0.073. Okay. But in the spirit of true programming, I chose in the slides not to do that, and instead of that, I'm going to basically refer, instead of hard coding numbers 153 and 177, the count of category of interest and the sample size. My category of interest counts all of them, all the counts I have already, right, in the variable state farm summary. So satisfied, no, there it is, right? Satisfied, the count was 153. Unsatisfied, the count was 24. How can I access these two numbers? Remember our discussion 5 minutes ago? When I run the function table, it gives me back the vector of values, right? And the vector elements, I have two, they're accessed by specifying the index, right? So the first element of the vector has the index number 1. Second element of the vector has index number 2, etc. Okay? So RStudio, or R language, generally speaking, is something that's called one-based index. Okay? So that means that each time when you have a vector, for example, your indexing starts with 1. Not all the languages are one-based languages. Python, for example, is zero-based index language. So that means that if you have a vector, the first element is going to be actually element number 0. That's the difference between Python and R in terms of how it handles vectors. Okay. So therefore, if I want, I'm going to replace 153, the count, with just first element of the vector set, state farm summary, right? State underscore farm summary. Okay, first element. That will give me the count of responses satisfied here. Responses satisfied, right? Okay. 177 is the sample size. I don't have sample size yet, right? So let me go ahead and do that. Sample size. We did that before several times. Sample size is just simply, I'm going to use the same letter n, right? Function is called n row, number of rows, in my data frame. And the data frame is called state farm data. This is my data frame. And let's just check, just to make sure that I got it right. N is 177. That is correct. So now instead of here 177, I can just say n. And my hypothesized proportion in the null and alternative is 0.9. Alternative is less. I'm going to run it again, and I should get the same exact output, right? No difference really. Yep, there it is. 0.07309 is my p-value. Okay. So now what do I do? Interpretation of this p-value is just like what we did before, right? If the true null, if the true population proportion is 0.9, 90% of customers are satisfied with the service, right? Then the likelihood to see the sample like this with the proportion of satisfied customers of 0.8644 or less. Why less? Because that's what the alternative says. This probability is 0.07309, right? So that's my interpretation of the p-value. Probability to see the sample like that, or even more extreme, if the null is true. Again, p-value is the probability. That's the interpretation. Okay, that's why it says p-value. P stands for probability. Okay, now I have to decide if the probability to see sample like that, or even more extreme, is not low, then it's consistent with null, and null stays. I don't reject it, right? If the probability to see sample like that, or even more extreme, is low, that means that, yeah, probably it points to the fact that my null should be rejected, right, in favor of alternative. How do I judge if this probability is low or not? I compare that against my measure, my measure of what's low probability and what's high probability, which is significance level. Well, which significance level do I use in this problem? It says 5%. Okay, so in my case then, 0.073 is greater than 0.05. P-value is higher than alpha. Likelihood to see sample like that is not small. Therefore, it's not very rare event. And I claim that this is consistent with my null hypothesis. Every once in a while I'll see a sample like that or even worse. And it's not unusual, even if the null is true. So therefore, conclusion of the test here is that p-value is higher than alpha. Therefore, I fail to reject the null. The sample collected does not provide me with evidence that the true satisfaction level in the population is less than 90%, or proportion of satisfied customers is under 0.9. Okay, so the statement by the State Farm Insurance that at least 90% of customers are satisfied, this sample failed to provide an evidence to claim that this statement is not true, right? So therefore, innocent until proven guilty, right? So sample does not provide me evidence otherwise, and their claim that at least 90% customers are satisfied still stands. Okay. So that concludes our lecture, and in the next lecture we're going to take a look at a more complicated case. Okay, and we're going to start the next lecture with actually the tool that we will use throughout the rest of this semester, and this is called analysis flowchart. So I'm going to stop the recording right there and see you in the next lecture.